all. Today's topic is stability of complexes. We know that most of the complex ions are stable. However, they dissociate into a slight extent. For example, if a complex, a general example, that is, if a complex MLN dissociate into M plus and L, that is NL, here we know that after some time there is an equilibrium is attained, and the equilibrium constant here we represented as dissociation constant. That means here the reaction takes place is dissociation. Here the complex MLN is dissociate into ions M plus and ligands. Therefore, we write the equilibrium constant as K dissociation, and we all know that the equilibrium constant is expressed in terms of concentration. That means concentration of products divided by concentration of reactants. That is concentration of M plus into concentration of L raised to N divided by concentration of MLN. That is the dissociation constant. If the complex is highly stable, then also there is a slight excess of this reaction takes place. And here we know that if the dissociation constant is higher, that means the complex is less stable. That is, if the dissociation constant is higher, that means the complex is get dissociated into its own ions. That means its stability is low. That's why it gets dissociated. And if the dissociation constant is less, that means the complex would be more stable. That is, here the dissociation constant and stability constant are inversely proportional. If dissociation constant increases, there is a decrease in the stability, and if dissociation constant decreases, there will be increase of stability. So that we can represent like this. That is, the central metal ion combines with ligands to form a complex ML4. Here we reverse the reaction. In this, the equilibrium constant we can represent it as formation constant. Here the metal complex is formed. That is why the equilibrium constant is represented as formation constant, and we can also write this formation constant in terms of concentration. Here the opposite, the reverse cases occur. That means Kf is equal to, we know that concentration of ML4 or MLN divided by concentration of M into concentration of L raised to 4 or L raised to N. That means here the reciprocal takes place. That is why we can write Kf is equal to 1 by K dissociation. Here the formation constant is also called stability constant. Therefore, formation constant and dissociation constant is inversely proportional. Here, if Kf, that means stability constant, is higher, there is higher stability of the complex. And we can write an example. Cu2 plus 4NH3 gives CuNH3 4 times 2 plus. Here the formation constant, that is stability constant, is represented like this. K is equal to CuNH3 4 times 2 plus divided by Cu2 plus into NH3 raised to 4. Okay. Here a complex is formed not in a single step. It occurs through a stepwise manner. In this, it is shown that if a metal ion combines with a single ligand to form Ml, and this is the first step, and we represented the stability constant as K1. That is first stability constant. And the second step, the complex Ml is again combined with the next ligand to form Ml2. Here the stability constant is K2. And third step, Ml2 combines with the next ligand to form Ml3. Here the stability constant is K3 and the reaction proceeds if MLn minus 1. That is, we are representing the complex is MLn. That's why here we write MLn minus 1 plus ligand giving MLn, and the stability constant is Kn. Here also we can write K1 as concentration of ml divided by m into L. Concentration of ml divided by concentration of m into concentration of L, and also K2 is equal to concentration of ml2 divided by concentration of ml into L, and also K3 is equal to ml2 divided by ml2 into L. And the last step, Kn is equal to mln divided by mln minus 1 into L. Here the stability constant K1, K2, K3, etc. Kn are called stepwise stability constant or stepwise formation constant. K1, K2, K3, etc. are called stepwise stability constant or stepwise formation constant. And also we can write this reaction in a single step, that is M plus 4L or NL gives MN, MLN or ML4. Like that, we can write this reaction in a single step, and the stability constant here we can represent it as beta. This beta is called overall stability constant. K1, K2, K3 are called stepwise stability constant, and if the reaction is written in the single step, then the whole stability constant, it is called overall stability constant, and we can represent or we can write the overall stability constant in terms of beta. Here the 4 steps are there, that's why B4 is given, and here beta 4 is equal to ML4 divided by M into L raised to 4. And also beta 4 is equal to K1 into K2 into K3 into K4. That means the overall stability constant is the product of stepwise stability constant, and generally we can write like this, that is beta n is equal to K1 into K2 into K3 into etc. Kn. That means the overall stability constant is the product of the stepwise stability constant. Okay. And also we can take logarithm on both sides, that is log beta n is equal to log K1 plus log K2 plus log K3 plus etc. We can write like that also. Let us take an example. CuH2O 4 times 2 plus. Here the complex is CuH2O 4 times 2 plus. Here the NH3 ligand replaces each water molecule in each step. In the first step, one NH3 molecule replaces one H2O molecule and forming CuH2O thrice NH3. Here one water molecule is eliminated and new complex is formed, and the first step, the stability constant is expressed as K1 or log K1 is here, log K1 is equal to 4.22. And in the next step, the next NH3 molecule replaces the water molecule and forming CuH2O twice, NH3 twice, and one water molecule is again eliminated, and here the stepwise stability constant is K2, and the value of log K2 is equal to 3.50, and the next step, the again NH3 molecule replaces one water molecule, and here the stepwise stability constant is log K3, and the value is 2.92, and at the last step all the water molecules are substituted by NH3 molecules, and the complex CuNH3 4 times 2 plus is formed. Here log K4 is equal to 2.18. From this example, we can see that the stepwise stability constant value decreases from top to bottom. That means in the first step the stability constant is 4.22, and the next step it is decreases to 3.50, and third step it decreases to 2.92, and last step the value is 2.18. That is, from this we can generally say that K1 is always higher than K2, which is higher than K3, which is higher than K4. That means the first stability constant is always higher and its value decreases in each step. That's all about stability of complexes. Thank you.